Here is the combined summary. The Logic Distillation (LD) framework is proposed to empower smaller language models (S-LLMs) with the planning and decision-making capabilities of larger language models (L-LLMs). L-LLMs exhibit superior performance in logical reasoning and planning tasks, but their large computational requirements make them impractical for deployment. S-LLMs, on the other hand, are more deployable but lack the capabilities of L-LLMs. The existing knowledge distillation (KD) approach has limitations, as S-LLMs merely mimic the outputs of L-LLMs without comprehending the underlying logic, leading to poor performance in planning and decision-making tasks. The LD framework decomposes the planning and decision-making logic of L-LLMs into multiple stages, each represented by a specific code function. LD integrates these functions into a function base and fine-tunes S-LLMs to learn and apply the relevant functions. During testing, LD employs a retriever to identify the top K relevant functions based on the current state and instructions, enabling S-LLMs to select and execute functions from this set. The LD framework consists of three components: L-LLMs, retriever, and S-LLMs. L-LLMs construct a function base, including a user manual that explains the usage of these functions. The retriever retrieves the top K functions based on the instructions and states, and S-LLMs select the appropriate functions for different stages of the task. The LD framework is summarized in Algorithm 1, which details the process of generating functions, building a function base, and selecting the most suitable function for each stage. The paper also discusses the advantages of selection over generation for S-LLMs, as it reduces the entropy of the prediction. Using the Lagrange multiplier method, the optimal probability distribution for each token in the token list can be calculated. The proposed LD method preserves more general capabilities of LLMs compared to knowledge distillation, which requires S-LLMs to memorize massive ILMS outputs. The paper introduces a novel approach to enhance the planning and decision-making capabilities of small language models, S-LLMs, using large language models, L-LLMs, as teachers. This method, called learning from decomposition, LD, allows the L-LLM to decompose the rules and instantiate the planning and decision-making logic into multiple functions, creating a user manual for the S-LLM to learn how to utilize these functions. The effectiveness of LD is demonstrated through experiments on a pursuit game, where S-LLM with LD outperforms L-LLM and S-LLM with knowledge distillation, KD, in both local and global perspectives. In the pursuit game with emergencies, L-LLM achieves a success rate of 90%, while S-LLM with KD has a success rate of 52%. However, S-LLM with LD surpasses L-LLM, achieving a success rate exceeding 90% and requiring an average of 4 fewer steps than the baselines. The paper also validates the effectiveness of converting logic into functions by examining the comprehensive planning and decision-making processes of L-LLM and S-LLM with LD. The proposed LD method addresses the limitations of larger LLMs, which are difficult to deploy due to their parameter scale, and smaller open-source LLMs, which fall short in performance. By enabling S-LLMs to comprehend the usage of each function, LD makes them more effective in planning and decision-making. The paper provides a comprehensive overview of existing research in the field of LLMs, including knowledge distillation, CodeBERT, and foundation models. Recent advancements in large language models have led to significant improvements in natural language processing tasks, such as text generation, language translation, and question answering, but require massive computational resources, large datasets, and substantial human feedback. Studies have demonstrated their potential in various domains, including medicine, finance, and healthcare, with examples such as Peng et al.'s exploration of generative language models in medical research and healthcare, Thirunavakarasu et al.'s discussion of large language models in medicine, and Wu et al.'s proposal of Bloomberg GPT for finance. The rise of large language models has led to the development of more advanced models, such as Llama 2, which offers open foundation and fine-tuned chat models. Surveys by Shi et al. And Xu et al. highlight the potential of large language model-based agents and provide a comprehensive review of knowledge distillation techniques, respectively. Zhao et al.'s survey covers large language models' architectures, training objectives, and applications, as well as their challenges and limitations, including high computational costs, potential biases, and lack of interpretability. The standard formulation of the masked language modeling objective is represented by equation 1, where the model predicts the masked tokens based on the context. Knowledge distillation is introduced as a technique where a smaller student model is trained to mimic the behavior of a larger teacher model, enabling the transfer of knowledge from the teacher to the student. These concepts are crucial in understanding the capabilities and limitations of large language models, as well as their potential applications and future directions.